how many of you are here for seeing how analytics will impact your own vertical? Because let me just complete the question. The other part of the question is how many of you are here to switch fields into analytics? That's the other. So let's do switch first. Okay. This is, okay. A little more than half of the class. How many for utilizing analytics in your current domain? That's a slightly smaller, maybe 60-40. Okay. My own excitement with come in. See, we are starting batch. This is batch 8, right? We are starting batch 8 with a different kind of high, because July 31st, somebody ranked us. Without our knowledge, somebody ranked us. Not really ranked, put us in the company of august group of players in terms of big data certification, and that gave us a high, new high, and then your batch is starting there. So we feel very excited about that people have seen the utility of this, not only in the country but outside. And we feel excited by that. I was speaking to somebody, that one of our students that went to National University of Singapore after studying here, and he actually put it in writing that I didn't enjoy the NUS program as much as I enjoyed the INSOFE program. Yes, that's the way. This guy got into Twitter in Singapore. He got trained here and he wanted to do a master's, so he went to National University of Singapore. The fact that he did his certification here helped him get into the US and completed there, and he got into Twitter. What excited me about analytics? Okay, this was a time when I was in. Do we have a place? I was in IIT Chennai at the time, and the words data mining was not born then. This was between 88 and 90. Just entering IIT Chennai in 88, I did my BTech from REC Allahabad, now it's called NIT Allahabad, in computer science, and getting into IIT, and the lab there was a lab called Knowledge-Based Computing Systems Lab. That's what it was called at the time, Knowledge-Based Computing Systems. Some people call it Expert Systems. The focus at the time was extracting knowledge from a human being through a process called knowledge engineering. So you would sit with somebody who is, let's say, an expert doctor, and ask them how they do their diagnosis. And you try to put them in the form of if-then rules or equations if you can. And those then become the basis of an automated program which will try to mimic the diagnosis that the doctor does. Okay? So you had forward chaining engines, backward chaining engines, and I really got excited by that. I thought, we can really download all this knowledge from a human expert and put them in the form of rules, and lo and behold, you have something that functions as well as a human being, maybe in a limited domain. So I joined that KBCS lab, and what we were looking at that time was from manufacturing setup. Can we do? There is something called model-based physics and qualitative reasoning. What you do is, if you have a complex thing like an aircraft engine, can you describe it as components and their functionalities and combine them using physical equations? These physics equations do not use regular E equals mc squared type variables, but they use qualitative variables. So if pressure increases, temperature will decrease. That kind of qualitative description. Variables have qualitative behavior, and there's a whole area of physics for that. In artificial intelligence, it's called qualitative reasoning. And we did some work on that. And then I went to Johns Hopkins University. Up there, it was very clear to me that I wanted to be in this area of, say, intelligence, artificial intelligence, or building intelligence systems. There are two ways in which people approach artificial intelligence. Okay, one is where you want to mimic, in biological intelligence. There is intelligence in every cell. There is intelligence in every organism. So can we mimic that intelligence? Is a whole set of techniques in machine learning came about from the desire to mimic. For example, a neural network, a direct mimicking of what we think is there in biological organism. We have neurons. These neurons have interconnections that are, a very large number of interconnections. Neurons by themselves are very simple in their functionality, but the intelligence comes from the interconnections. So we want to mimic that and say, can we have simple processing units which can do just simple weighted sums and thresholding? A neuron cannot do that more than that. It does a weighted sum and thresholds that value. Take a neuron like that and connect it up in multiple, connect it up with a large neighborhood of other neurons. And when they communicate, these functions get accumulated. I can do some computation, you can do some computation. So I give you my result when you do the computation, then it's an accumulation of two computations. Like this, if I have billions of connections happening, it's an accumulation of billions of simple computations. And that can compute functions that none of your other models can do. So that's the motivation behind a neural network, trying to mimic what we think happens inside biological, intelligent machines. Another example is optimization. Ant colonies. Ant colonies work in a certain way. Bee colonies work in a certain way. Ants, again, simple function, but complex communication mechanisms through which you get an optimal solution to a problem very, very quickly. You drop a thing of sugar on the floor, they figure out in no time what the best way to get there is. And this is not an individual ant's intelligence, it is the intelligence of the society, of the colony. So can we have mechanisms where, for optimization, where we can utilize the same metaphor of simple organisms interacting to figure out the solution very, very rapidly, to figure out an optimal solution very rapidly. Okay, if there are little obstacles, they will figure out to go around that and come quite quickly. If you think about it, we are trying, when you build a Mars rover, okay, we want to compare an ant with a Mars rover. Mars rover is an unmanned, of course, vehicle which for the surface of Mars. Mars rover project is fairly old. It was funded by DARPA, Defense Advanced Research Project Agency, and the goal was for a vehicle to be able to navigate an unknown terrain, and it's likely that when you on certain geographies, if you put it on low gravity situations, it's a dynamic environment. It's not a fixed terrain. Once you take a picture, you cannot figure out a static algorithm to go around because things keep changing in your environment. So can you have autonomous vehicles when the obstacles are changing dynamically? This is a similar problem as ant colony optimization. So can we utilize this intelligence? Can we observe these colonies, convert it into equations, and utilize that in building these machines? So there's a whole group of learning research that works with mimicking natural intelligence. Because the best intelligence that we know today is natural intelligence. I want you to understand this. We do not know any better than what that leaf does today. It grows out of something. It figures out how to grow. An organism figures out how to grow, and in limited ways, but in very robust ways. Okay. Human intelligence, of course, several things that we can do today, our best systems cannot. Now, there is another group, another set of researchers, or another, body of researchers and practitioners in learning that believe that it doesn't matter. You don't need to mimic human or biological intelligence, as long as you can design systems that do what you want them to do, doesn't matter how you do them. They do not need to parallel anything that's going on in the nature. For example, if I want something to, let's say, figure out a diagnosis for a disease, if I can put in all the knowledge about the diseases and symptoms and other information that is needed, and if I can have an efficient search engine that can go and find the diagnosis for the set of symptoms that you are providing. Let's say a particular patient has certain symptoms and you want to know what is the disease. And if you have a large repository of symptoms and corresponding diseases, or what people thought were the likelihood of a disease when they saw certain symptoms, and if you can build a intelligent system that can go through and figure out the diagnosis, it doesn't have to mimic any natural intelligence. You see what I'm saying? People actually wrestled with this for a while, that should we try to emulate nature or should we just do engineering, intelligent engineering? This is engineering with intelligence, right? What intelligence? What we define as intelligence. If you, the definition of intelligence is quite hazy actually. How do you define intelligence? As long as you don't know how to do something, it appears intelligent. Once you know how to do it and somebody gives you a flow chart, it's no longer intelligent. Okay. So, but can we just focus on building systems that are intelligent and not worry about mimicking nature? And so in my own work, I decided to take the second path. I said, if you want to mimic biological systems, then you need to learn a lot about biological systems. That's a longer path. We engineers like to take shortcuts. So I wanted to just focus on building systems that can do things well. And then then I once sort of immersed in this, then I figured I saw how many areas you can apply this well. And I see this as some people have called data the fuel of the coming century. Have you heard this? Data is the petrol of the next century. Because things will be basically based on the intelligence of the juice that you extract from the data, then your organizations will take the right decisions, or individuals will take the right decisions, and so on. So people compare it with a very, very precious resource, data. And I tend to believe, I see the value. Of course, it's not all in data. Clearly, a lot of things are in people's heads. But where did that come into people's heads from? Because they have observed, they have experienced things in the world, and they have learned. So it's just that our learning systems do not have that level of abstraction today. But going forward, if we do have systems that can observe as much as we are observing from our childhood, and use as much intelligence as we are using to find patterns, to abstract out patterns, to get to sort of the crux of the matter in our own minds, then we will have systems that are as intelligent or more intelligent than us. So I see data as a really important direction. So I'm very happy that all of you decided to take that path. This is not just about career enhancement through big data, which is a side effect. You will have that. But it's also about a new way of approaching the science of computation. It's a new way of. There are two ways if you want to solve a problem. One is that you can think of an algorithm to solve that problem. I want to walk from this end to that corner to access something in that corner of the room. Then I'll have to see, which is the group of people that are easiest to ask to get up, and then I need to find my way. I need to, sort of navigate around the obstacles and get to where I want to get. This is an algorithm that I can follow. Okay. I have somebody doing, let's say, some transactions in my bank that are exhibiting some kind of fraud. How do I deal with this? Or how do I detect a transaction that is fraud? One way is to write down an algorithm that if somebody has been doing transactions in this range and suddenly does a transaction which is way outside that range, in terms of rupee value or in terms of geographic spread. Somebody who's operating in South India suddenly does a transaction in Mexico. Then maybe there's an alert that needs to be raised there. So you can actually write down an algorithm to detect fraud. This is one way. The second is, start with an assumption that I don't know what defines fraud. Fraud is defined by the data. So let me keep looking at transactions, that some data I'm collecting about the transaction and I'm finding out if it is fraud or not. Let me look at thousands of fraud and non-fraud transactions. From that, try and build a model for what is fraud. Okay. Same with the navigation. Look, I'll leave a robo here, ask it to go to that corner. Okay, build some randomization into the robo. First way it goes from there, second it goes from there. It tries multiple paths. Every time record the path it has taken and whether it has reached the target or not. This is your training set. Steps that it has taken, moves that it has made, whether it reached target or not. Like that, let it try out 1,000 times. From this, try and build an algorithm. Try and build a model of what steps lead to success. What sequence of steps leads to success. You see what I'm saying? Any problem can be seen from two different perspectives. One is algorithmic, one is data. Algorithm-centered perspective, another is data-centered perspective. From the data, can I extract my knowledge? That is what is data-centric perspective. Algorithm-centric is from my experience of the world, can I write down step by step how to solve this problem? Okay? For example, if I want to do a calculation, from my, I want to calculate compound interest. From my experience of the world, I know how to do this. I don't have to really go into the data to figure out a model of how to compute. It's possible. It's possible to build a model for computing compound interest. I'll give you how much money did they put in, how many months was the data with you, was the money with you, and how much interest did that person earn. If a bank just writes these numbers down, okay, a principal, how many years was that principal with me, and what interest did I pay out? If you write down an Excel sheet of these, just from this, without knowing your formula of compound interest, you can find out, you can build a model of computing compound interest for an unknown, for a next customer. So any problem can be seen as seen from the algorithmic perspective or a data perspective. Data is that fundamental. That's what I want you to know. How many of you studied computer science here? In some form or the other? That's about 75–80% of the class. Okay. What did the others, what is the background, educational background? Civil.
Chemical.
Mechanical.
Chemical.
Instrumentation.
Another instrumentation, your telecom, EI, electronics and instrumentation. EC, okay.
Commerce. Electrical.
Commerce, okay. Electrical.
Electronic.
Computer science, yes, computer science.
Statistics.
Statistics, okay.
Electronics.
Electronics and communication. Electronics and telecom is good. Okay. So, for those of you that have taken computer subjects, you know that algorithms are sort of basic to computer science, right? One of the first things you learn is we have to tell the computer how to do things. So, what we are looking at data, although the community today, the data sciences community outside is not talking in that, not talking philosophically at this level. I want you to understand that the reason we define data sciences as a different area of work is because we can find solutions in totally different ways using data science. Algorithmic sciences or computational sciences have so far been, have been algorithmic in nature. Data sciences give us a way of jumping out of that. Why is that important? Why do you think that is important? Why can't we just stick to the algorithmic way of doing things? Everyone knows what an algorithm is, those non-computer science folks. If anyone doesn't know, please interrupt me. See, this is a heterogeneous class, right? This is a diverse people with diverse backgrounds. So it's perfectly fine not to understand something that is going on in the class at a given point of time. Please ask, we will elaborate that. Anyone doesn't know what algorithm means? Everyone knows. So, algorithm is a step-by-step procedure for doing something. Step-by-step instructions, this which can be implemented. So, question is, why do we need an alternative? I'm saying that there is a whole way of doing things with algorithms, and we now have a new way of doing things using data. Even something like compound interest, you can ditch your algorithm, just look at an Excel sheet of data and build a model of computing. Do your regressions or whatever you want to do. Do a model where interest can be computed based on past data. Super. Might be to save time. If you already know how to do it, why go through this whole...
The number of dimensions you can take into account using the data and the external factors which your experience will not come into use when you're developing the algorithm. So maybe that.
And you may discover new knowledge from the data, of the patterns from the data, which is not immediately implicit or explicit in the experience.
Right.
Data is
So you're, when you say saved data, you were talking in favor of the algorithm camp.
actually what happens. Suppose we are writing an algorithm. So different algorithms will rewrite depending upon the nature of algorithm. It takes different time to execution.
Correct.
That complexity increase every day. Suppose for example we are using 2 or 3 for loops inside another. So the execution time increases.
Correct.
But what happens if we have a cluster of data? So instead of going through the algorithm, we can just look at the same variables and pick up the result without waiting for the algorithm to execute.
So you actually think that the data-based approach will be faster than
Not
the algorithm,
But not accurate. Because actually you give an example.
but not accurate.
Yeah, because you give an example.
No, let's stick to speed. We'll go to the next point. So speed is the speed. You feel that the data-based approach is faster than the algorithm-based approach?
I think so.
Would you agree with that? Yeah? One can argue it both ways, right? If I know exactly how to go to that corner, I will be faster just implementing that rather than looking at, let's say, 1,000 instances of a robo failing to get there and trying to figure out the best path from there. If I know the solution and I can put it in as an algorithm, then I'm better off using that algorithm. But if I do not know the solution, then figuring out an algorithm takes longer than going through the data. So it's for things where we don't know the solution. This is one point. You said that there are things that you may not be able to do through the algorithm.
No, there are some hidden patterns inside the data which we may not be aware with our experience.
Yes.
So those, we are discovering some new knowledge from the data.
Correct. Correct.
Data has
So it's novel patterns that you don't know. You may be able to unearth by looking at data. Okay. Somebody else.
data is more informative, or it's like
Data has more than the algorithm.
more. See, algorithm is based mainly on the knowledge of the person who is writing it,
Hmm.
person or a team. But data is like it's a whole big thing, bigger thing, wherein we have more information.
Okay. And likewise, a counterpoint to this, we are just trying to, make all the points. So, an opposite, if I am a devil's advocate, I say data also has a lot of unnecessary things in it, right? When I am trying to drive on the road, let's say a two-wheeler or a four-wheeler, then there's so much of data that I am capturing that, in terms of pixels. If you just simply look at the number of pixels, human eye can do some 120 degrees. And in these 120 degrees, all the pixels that I am acquiring is so much of data. That is every frame, 16 frames per second or whatever number of frames that human eye takes in. And for the duration that I am driving, this is a huge amount of data I take in. Out of which, because I have certain experience, I've figured out what to not focus on. Figured out what to ignore. Figuring out what to ignore is intelligence. Right? It's actually a very necessary part of intelligence. So data is so much of unnecessary information that we need to teach our systems to ignore data, ignore some data.
Conditions are changing with time. You can't keep changing your algorithms.
Conditions are changing, absolutely. Sorry, I didn't even start. You can, in other words, you can build dynamic systems much better using data than using algorithms. The responsive systems that can look, as your data changes, if your system can change based on that, then you build much more responsive systems. Sorry.
Just to add to it, you are providing a model or logic for your problem instead of just taking a solution and then trying to address your problem. So customized, more customized for your scenario.
Yeah, because your data is very, very specific to you, and you can build a more tailor-made solution if you focus on the data instead of focusing on the algorithm. Now, we are really not pitching or pegging algorithm against data here. We would like to take advantage of algorithms where we can, but we are trying to identify situations where algorithms may fall short, where data science is needed. That's what we are trying to do in this sort of discussion. There are situations where algorithms fall short, and we will try and write down those situations. One is where you want tailor-made solutions. Second, where you want dynamic solutions, solutions that keep changing based on the nature of data. Can you give an example of that? Solutions that need to change when your data changes? Something, a simple example that others can understand. Disease escape changing, diagnosis? Correct. So anything where natural systems are involved, because that system is adapting, algorithms need to adapt to that, right? Another type of virus is computer viruses. You make antivirus software, people who are making viruses make even stronger viruses, then you make stronger antivirus software, this keeps going. Yeah? Wherever there are two intelligent organisms working against each other, police robber game happens. Right? Robbers get smarter, police have to get smarter, and so on and so forth. This is an ongoing cycle. So dynamic systems. So whenever you want security systems, you want automated, virus detection, or you want diagnosis systems, spam, another police robber thing. People who are spamming want to keep spamming in ways that your anti-spam software does not detect. So you have to keep making your anti-spam software better. That is another place where you need dynamic, data-dependent method generation and not a hard-coded static method.
The automated cars.
Automated cars, because the environment keeps changing and you need to take decisions dynamically. Okay? And we also said that where the algorithm itself is not clear, the point that you have made.
Solution is not.
Sorry?
When we are not, we don't know what solution we need.
Okay. Solution unknown. This is a different category. Can you give an example for solution unknown? Solution can't be described. We don't know the algorithm.
An automatic car going in a way need to figure out based on the traffic or obstacles and reach a place that can take a different route.
Car, when we say solution unknown, we are system builders. So we go and ask a driver, how are you deciding what to do? Then I think as a driver, many of you must be driving, so I think you may be able to say that when an obstacle comes in so much of distance, then I brake. When something comes, I swerve. These kinds of things we will be able to list out. As long as our car can find out what the obstacles are, then it can utilize that knowledge from you. But there are situations where you just cannot verbalize, describe your knowledge. You ask a doctor sees a patient just by looking at the patient, or just by looking at a X-ray or a MRI of the patient, has a feel that this person seems to have a problem here. Okay? People have done these experiments. They sat with radiologists and asked them, how do you know this? And the radiologist doesn't know. There is a precognitive thing that is happening. In the brain, there is cognition is thinking. So cognition is thinking that you are aware of. Then there is precognition, which is thinking that you are unaware of. Let us say you are very, very interested in cars, in new cars. When you are driving on the highway, you spot new cars. Somebody sitting next to you who doesn't care about a Jaguar may not spot it. And if I am very interested in hoardings, in the most crowded traffic, I'll still see that hoarding. Because there is precognition happening. Okay? Things that people cannot describe. And a lot of intelligent action depends upon what people do at the precognitive stage. A fund manager looks at some data and suddenly has an intuition. How do you capture that? You cannot algorithmically capture it. You may be able to capture it in data science. So data science is useful, sir.
Normally when we want to predict something, probably algorithms may fall short actually. Let's say for example, in the next few hours what is going to happen based on the data I have, I can tell, but I may not tell through algorithms.
Yes, if you do not know what is going to happen, and if your data has enough, if you have enough data to predict that, maybe your predictive systems will do better. If I am going to, but some things are, it's possible to do algorithmically. Assuming that there are no unseen factors, train leaves station X at so much time, what time will it reach this station, what time will it reach this station? This type of path planning can be done, or schedule planning can be done algorithmically. Algorithmically, a lot of things can be done. In fact, today, if you look at it, most of the implemented systems are algorithmic. They're not, systems that are based on data are much less than systems that are based on algorithms today. So algorithms are pretty useful for talking about past, present and future. Algorithms are pretty useful. But now when the complexity of systems increases, and when we have to deal with unknown solutions, I mean, you see me today, tomorrow I come with a beard, will you recognize me? It's not, I'm not talking about a movie disguise. Regular beard grows and I come here. I don't think you will fail to recognize me. Correct? We are very good at recognizing people. 15 years ago you see somebody, the college classmate, 15, 20 years later, we see them again. This time we had a reunion, a 25-year reunion last November. So 150 of us from the BTech batch, again came to Hyderabad. We have not seen many of these people. And immediately the face makes sense, and none of them look the same. They all have double chins, triple chins now, like me. But you can recognize them. So if I ask you to describe how do you recognize a face, you cannot. Right? People tried this. There may be different points that you are looking at in the face, different contours, and those remain static. It's not easy to remember. It's not easy to describe. Remember, yes, but you can't describe. So when solutions cannot be described, when they are dynamic, when solution needs to be tailor-made to that situation. I don't mean to an organization. Tailor-made in the sense, let's say American Express card. Transaction, somebody swipes it. Should I approve this or not? Depends on what transactions they have done just in the past, what transactions people like that have done in the past. Okay? Based on that, you want to give a dynamic yes or no to this. This is very, very tailor-made decision. For such things, data-centric decisions would be better than purely algorithmic decisions. That's the relevance of data science. And decisions like these are increasing today because of the enormous amounts of data that we are producing. Decisions like these are increasing.
Sometimes you may need data to define an algorithm.
Yeah, what combination of it?
Combination.
Based on the data, you arrive at an algorithm.
Absolutely, you do. In all that model building is for that only. Yeah, using models, we'll say, okay, I want to predict what. Since nobody here in agriculture, I'll take an agriculture example. I want to predict how much of paddy we'll produce as a state next year. Based on the data of what the rainfall is, how many acres of land, blah blah blah, how much of forestation, all the factors, I will come up with a regression model to predict the amount. Regression is just an equation. Come within first degree or second degree equation to predict the amount of paddy. Once the equation comes in, it becomes an algorithm because you then just code that implementation. Yeah. So the whole cycle is when you're doing data science. We first said algorithm centric versus data centric. This is where our discussion started. Then we said it's not really versus, it is plus data centric, algorithm centric and data centric, because this is useful in some cases, this is useful in some cases. Okay. And the way data centric works is you have some data and you build a model from it using a variety of algorithms, some of which we will be going in detail in this class. And then this model becomes an algorithm. Model is nothing but, many of the models can be written down, even neural networks can be written down as a computation, as a step-by-step computation. I mean, unless it's a step-by-step computation, today we don't have mechanisms of implementing it. All our computers follow a Turing machine model. Reverse engineering from the data. Exactly. You see the world, you figure out the solution.
I didn't get how you can make a model without an algorithm.
You have to use an algorithm, but it's a different. Okay. We are talking about two different algorithms here. The algorithm for a robot to navigate to that end of the room is what we want to find. Then there is a neural network algorithm, which is how do you update the weights of a neural network based on the data. This algorithm you must have to learn this algorithm. Each of the methods that we talk about, decision trees or regression or neural networks or any of these methods are individual algorithms themselves. But the input to that is the data, output is a model. That model is the algorithm that you need for another problem.
It's like building a combination of algorithms into a model based on the data and using that as a one unit. Using that model as one unit.
Yeah, let me try and simplify that. Let's say there is a system here, some system which has some inputs. Based on the inputs, it produces certain outputs. A very generic view. This could be a system that is a face recognition system. The input is a face, the output is, this is, Narendra Modi. Output, this is this person, X. This could be a driving system where inputs are all the images or inputs that you are taking in at the time of driving, and this is a decision that you make on what to do next. I apply my brakes or I accelerate or whatever it is. So, a generic system, algorithmic approach assumes that it knows this. It knows what is in the system. That my system is, you do this step, then you do this step, then you do this step. That calculation, it assumes that it knows. So, for an algorithmic approach, Okay, I want to do compound interest calculation. I know my principal, I know my rate of interest, I know my period of loan, and the system is the compound interest calculation method. I know the equation. Knowing these two, I compute this. So, in the algorithm approach, we assume that these are known, and this is the algorithm. So, this is what is computed in the algorithmic approach. Okay? In the data-centric approach, data science approach, we know this and this. We don't know this. You know amount, period, and rate of interest. You know how much interest was paid up. You don't know the equation, and you figure out the equation. Does it make sense? So these two are known, and this is computed in the data set.
I just have a question. Is it possible that using the data science approach, we can come up with some different equation which gives the same result?
Yeah, there are. See, here it is a more restricted thing. When you know the system, when you know the equation, you produce the output. It's more like applying an equation and getting out the results. But if you know the inputs and outputs and you're trying to figure out the system, there are infinite possible systems that would have generated the same output. Isn't it? So the task here becomes that of picking one among these large number of possible systems. So absolutely, you're right on dot there.
To be simple, that is like inductive and deductive learning.
Correct. Deductive and inductive are the words that are utilized in the logic. From the logic theory, we borrow those two words into learning. Yeah.
Is it an accepted thesis that the data science can be developed or it's
It's not an accepted case. It is just a different paradigm that is useful in cases where algorithms may not be adequate. We are not doing a versus here at all. That's why I took out that word. There are situations where we know for a fact that we cannot write an algorithm, like face recognition or automated driving of a vehicle. You must have a data-centric system. In fact, going forward, what I think will happen is the distinction between both of these will become hazier. There will be systems that will incorporate both algorithmic and data science components inside. Today, because data science is still in its adolescence, you hear about it separately. When it matures, it will mingle.
as of now, do you have any solution which is designed from data science perspective which is better than the
Yes, many, and I'll show you many examples. Absolutely, many. We are not saying that data science approach does not need algorithms. To one of you made a point. To compute this system, you need another algorithm. So we are not going away from algorithms here, but it's just that the center, the anchor, is the data here in this approach. The anchor is the algorithm. Okay, that I have already said where I am coming